Hey, welcome back. In this video, in this lesson, you're going to be learning about proof. Proof is a pretty big deal in the math world, right?
Proof is what separates mathematics from all the other subjects, especially if you look at sciences, they're always looking at hypotheses and getting closer to hypotheses. Mathematics is absolute.
So we're going to go through what is a proof. We're going to walk you through three different types of proof. The first one being deductive, which is probably what you're more familiar with. You'll see things like Pythagorean theorem and quadratic formula there. And we'll do proof by contradiction, which is actually very fascinating. It assumes that it's something you know it's not true, and then you find a contradiction somewhere in the argument. And then the last one, which is in your IB syllabus, the higher level, is proof by induction, which is what we're working for today. So, proof. What is a proof?
Good. So a mathematical proof is a convincing demonstration using accepted mathematical arguments that a mathematical statement is necessarily true, and true being absolutely true.
So without a single exception. So this is a proof, meaning you cannot have a rebuttal. You cannot argue this. It's proof and there's no exceptions. So the first type of proof is a deductive proof. And we're going to jump over to here. And our first proof is we're going to try and show you that the sum of all the angles in a triangle, any triangle, is 180 degrees.
Interesting. So how are we going to go about this?
Well, the first thing you need to understand is that you have to have some sort of algebraic proof for this, because there's an infinite amount of triangles. We can't just add up all possible angles of every single triangle, because there's infinitely many. So we have to have another technique, and that's where the proof comes in here. We're going to use what's called alternate interior angles. So the first assumption is that this line right here, AB, is parallel to ED, right?
Okay.
So then we're going to just take a line like this, not a very good line, and we're going to cut AB, and we're going to cut ED. So that means that this is this angle and this angle are the same. Those are called vertical angles. And that also means that this angle, which is equal to this angle, is also the same as this angle. That's called alternate interior. So this angle right here, ECA, is the same as just angle A, right?
Excellent.
Okay, so we can use that same argument for this. We can say that this angle, if we draw a line like this, sorry, I went too far. This angle right here is the same as this angle because they're vertical angles.
Okay, vertically opposite, good.
Yeah, and then that's the same as angle B. So that this angle right here is the same as angle B.
Okay, so alternate interior, good.
Alternate interior, correct. So let's write this out.
And those terms we knew from middle school.
From middle school, yeah. So we have ECA, so angle ECA plus angle ACB plus angle DCB. Okay, we know that this equals what? We know that this equals 180 degrees, right? Because it's just a straight line. This angle plus this angle plus this angle is just a straight line. But we just said that this angle is the same as angle A. So this is angle A. This angle, ACB, well, we'll just rewrite it as angle C. And then this angle, DCB, which we wrote right here, is the same as angle B.
And those are the three angles inside the triangle.
Correct. And this, of course, is the same, which equals 180 degrees. This is a proof. We just proved that the three angles in a triangle add up to 180 degrees.
Good.
So we don't have to do any other triangles.
So we built on some knowledge that we knew. We knew some parallel line theorems. We knew that angles on a line add up to 180. We took that information and we proved a new theorem, building on existing knowledge, that the angles in a triangle add up to 180.
So next, we move on to proof by contradiction. This is one of my favorites. This is very cool. So, one of the oldest proofs by contradiction is to prove that the square root of 2 is irrational. Well, let's first define what some of these things are. What is irrational?
So irrational is a number that cannot be written as a over b, where a and b are both integers.
Right. So, yeah, like a ratio. It cannot be expressed as a fraction.
Mm-hmm.
Okay. Well, there's a funny little story about this. Not funny. It's actually someone died, but
Well, not funny for her passes.
yeah. So, what is it?
Well, back in the days, the Pythagoreans, they believed that all things could be represented by rational numbers, and they had a real elegance about it, and it was almost religion to them. And Hippasus discovered that actually there are some numbers that you cannot write as a ratio a over b of two integers.
And this really upset Pythagoras because, like Mr. Kerber said, Pythagoras thought in his school, one of the foundations of his school thought that every number could be expressed as a fraction. Every single number. And that was a big theory of theirs, and they taught that. And this guy said, well, if you take a square and you cut it in half, where the lengths of the square are 1 by 1, and you use the Pythagorean theorem that was developed at the school, then this side is square root of 2. Correct? And, well, that's sort of weird. If this is irrational, that means it's a decimal that never, ever ends, which is sort of contradictory in itself. How can you have a length, a number that never ends, but yet I can see the length right here?
And this rocked their world at that time, and they were so upset that the story has, several different myths to it, but apparently they took him out in a boat and killed him.
Threw him over the edge.
Mm-hmm.
Yeah, and he died. So whether it's true or not, nobody knows, and actually we don't really even know where this particular proof came from, this proof by contradiction. Nobody's particularly accredited to it, but it is pretty cool. So let's get started. So we're going to take square root of 2, and we're going to assume that it actually is rational. So a over b. And this, a over b, is the lowest possible fraction, which means that a and b are relatively prime to each other, so lowest possible fraction. Mm-hmm. So some examples of lowest possible fractions could be like 3 over 5, 2 over 7, 1 over 9. But what's not an example of a lowest fraction would be something like 2 over 4.
Mm-hmm.
Why not?
Because you can reduce it, divide the top and bottom by 2 and get 1/2.
Right. So remember this. We're going to use this. This is not a lowest fraction. They're both even, basically.
Mm-hmm.
Both the top and the bottom are even, which forces it. You could take a 2 out of both the numerator and the denominator. Okay, so let's keep going. So let's square both sides. We get 2 equals a squared over b squared. Okay. And then we have
over b squared?
b squared, sorry. And then we have 2b squared equals a squared, right? So this is 2 times b squared. 2 times some number is a squared. That forces a squared to be even.
Mm-hmm.
Okay? And if a squared is even, this is a very small proof. I won't go through it now, but it's really easy to prove. If a squared is even, that means a is even.
Mm-hmm.
Okay, we got that much? So now, if a is even, I'm going to rewrite a as a 2 times c.
Okay, introduce, good.
It's even.
Mm-hmm.
Okay, this forces a to be even. Well, it is even. Okay, so now I'm going to take out a. I'm going to put in 2c. So now I have 2b squared equals 2c squared. Right?
Mm-hmm.
So then that's 2b squared equals 4c squared. Just distribute that squared. All right, so now I'll divide by 2. So then I have b squared is equal to 2c squared. Well, what did we just talk about? B squared is 2 times some number. That means b squared is even, which means b is even, which means that a divide b, if both a is even and b is even, then our very, very first assumption that this is the lowest possible fraction is false.
And hence our contradiction.
And hence the contradiction. Now, we don't actually have to find what square root of 2 is, but the technique is just to find something wrong with our initial argument, and that's it. So we proved that square root of 2 is irrational. I know this is hard to sit with, but it's valid.
And it's airtight. Proof by contradiction, the first time that I saw this, I was like, wow, you know, and you think it through, and then you see it. And it's quite an elegant way to sometimes prove things that you can't see a different way out of. And every once in a while, this will come in really handy.
Yeah, especially when you can't prove it any other way.
Exactly.
Okay. And the last proof we're going to talk about today, which is the one that you are responsible for knowing in the higher level, is called proof by induction.
This is and there's a nice, elegant analogy for the inductive proofs, which links back to the dominoes. Let's introduce some notation and get started.
Yeah, so we have the first step. The first step is P1.
Okay, and P stands for?
Proposition.
Okay.
So the first step is we show that the first domino falls. So P1, we show that it falls. Okay, and then the second step is we assume some kth domino falls. This is an assumption. We're assuming that it falls. And then the third step is we show that the next domino right after the kth domino falls. Now, I know this probably sounds quite, weird right now, but basically what this means is that we have a formula. We recognized a pattern. We have a pattern, and then we develop a formula, and then if we can't figure out some sort of deductive proof, then our next option is to go to an inductive proof. And if we assume that the kth step will fall, and then we show that the next step falls, then the formula must work.
For every single case. So if you can show it for k and k plus 1, that means you can show it for 20 and 21. You can show it for 2 and 3. You can show it for 12,000 and 12,001. Yeah. It will always knock the next one over. So mathematicians love this. They love to look at patterns, find patterns, try to generalize those patterns, and then the ultimate is when you can actually prove that pattern works always.
So we're going to start with probably one of the more easy mathematical induction proofs, and that's to sum the first n integers. But you've seen this before, right? We've done this already.
And this is related to the sequence and series unit.
So this is actually an arithmetic series. Okay, so we're saying that p sub n, where n is the first n integers, is 1 plus 2 plus 3 plus all the way out to the nth one, however many I want. And we're saying that this equals n over 2, 1 plus n. Now let's actually do this with an arithmetic series.
Okay.
So P1 is 1. And then we have D, the common difference, is also 1, right? So then we have the formula. So Pn is equal to n over 2, 1 plus un, which is 1 plus n minus 1, times d. Is that right?
Okay.
So then that's n over 2 times 2 plus n minus 1. So that's n over 2, 1 plus n. Okay, this is review. This is the arithmetic series. So now we know this is true. This is a deductive proof for this. We're seeing it work right now. Now we're going to say, okay, well, let's do it with an inductive proof. So let's say we can't do this particular problem deductively. It's too difficult, or we can't do it in general. So we have our next best option is an inductive proof.
Okay. And we start off then trying to show that it's true for the first domino, P1.
Okay, P1. So we're going to do the left hand side first. So we always do left hand side, right hand side. It's pretty common to do this. So the left hand side is 1. We know that. Okay, that's the first integer.
Okay.
The right hand side is here. This is the right. So that's 1 over 2, 1 plus 1. So that's 1 over 2 times 2, which is in fact 1.
Good. And it seems so logical that this first step is usually quite simple, the algebra falls out, but it's very important that you show that it's true for 1. It seems trivial, but it's important because you have to show that first one works. And you don't start by saying 1 equals 1. You have to start clearly indicating that you're working on the left-hand side and the right-hand side and come to the point that they're the same.
Yeah, you never want to get to a point in any sort of mathematics that 1 equals 1. There's no point in that. We know 1 equals 1.
Yeah.
So yeah, work with the left-hand side and then work with the right-hand side and show that they're the same, which they are. And actually sometimes you'll see books have a little check mark right there. Okay, so now the first domino has fallen. So the next domino is to assume P sub k is true.
Okay.
Which means that I have a 1 plus 2 plus 3 plus all out to the kth domino is equal to k over 2, 1 plus k.
Okay, and here we can connect them with an equals because we're assuming that this is true.
We're assuming it's true, yeah. So this right here, in fact this whole thing, is going to be our substitution. There's always a substitution happening in induction. And it's really important that you identify that because most people with the start of induction, they forget this step. Okay.
And if you forget it, you can often end up in some very messy situations. You really try to think that's your goal at some point.
So now, we're going to go on to step number 3. Show true for pk plus 1. Okay, so now we have 1 plus 2 plus 3 plus all the way out to k. K plus k plus 1. And this should be, we don't know, but this should be k plus 1 over 2. And then this is 1 plus k plus 1.
Okay.
Which is k plus 1 over 2 times 2 plus k.
Okay, and notice that here it's equals with a question mark. You can either set up left-hand side, right-hand side again, or equals with a question mark, but do not say these things are equal. Not until you've proven them.
No, we do not know. And I like to highlight this as well, and I like to put goal.
Okay.
So they know, whoever's reading your paper, that this is a goal. And like Mr. Kurbis just said, put a question mark, and this is the only time you're gonna write the goal until the end when you've actually proved it. So don't follow it down the whole time. Nobody likes to see that. Okay, so now we can do the inductive step. Well, what do we see?
Okay, so we should always work with what we assumed at some point. It doesn't always fall out so nicely in the first step, but it always, at some point, you want to make that substitution pointed out earlier. So there, it sits very clearly that from our assumption, we can replace what's inside those red brackets with k over 2 times 1 plus k.
So this is we assume to be this. And then we have the next term, which is k plus 1.
Okay.
Okay. So now let's stop for a second and talk about this. This is our goal. This is what we assume to be true. This is our formula that we've recognized the pattern, and this is what we think the formula is for the sum of the first n integers. Now, we're going through the inductive step. If I follow the algebra all the way down here, if this was incorrect, if my initial assumption was incorrect, I would never get to this point. And that's the power of induction right there. If it's true, then this will happen. This will be my simplified version of this. If it's not true, I'll never reach it.
Yeah, it seems so obvious and so trivial when it falls out, but what's difficult to recognize is that if it doesn't fall out, it's not true. So the elegance of the proof is just so powerful. It's such a powerful technique.
Yeah.
And so these things look kind of similar, but not quite. What could we do here to make them work the left-hand side so it looks more like the right-hand side?
So what I'm going to do is I'm going to do a common denominator. Common denominator is the first basic technique for induction. It happens all the time, mostly because a lot of these are series. We're adding several terms, so a common denominator is definitely going to help here. So I'll start with that. So I have k, 1 plus k, plus 2, 1 plus k, I'll rewrite it in the same order, just like this, all over 2. All right. The second very important tip, very helpful tip, is factor by grouping. So we have a 1 plus k and a 1 plus k. So we can factor out a 1 plus k, and we get k plus 2 and 1 plus k.
Okay, so binomial common factor, factor it out, and suddenly,
look,
we have it.
It's done. K plus 1, k plus 1. 2 plus k, k plus 2. Same thing. So we have now proven this to be true. This is a true formula, and we have one more step. What's the step?
Very important for your final reasoning mark. You need to tie this all together. So you need a concluding statement. So since P1 is true, and we've shown pk plus 1 is true, whenever pk is true, it follows that pk is true for all positive integers.
So this is a statement that you can make pretty generic. Most inductive problems, if we go back up, don't have a pk in it. Just make it up. Just say that this statement here is pn, and then you can work with the pk's and pk plus 1s. And then you can really this can be your statement for all all inductive problems.
And there are different permutations, and a lot of your teacher might have a different concluding statement. The main important thing is that you follow these 4 steps, and you have some kind of template in your head as you walk through these problems.
All right, so there's your videos and instruction on proof.